All right, in this video we're going to do a sample problem using rotational kinetic energy. So we have a bike and it has a 10 kilogram frame, 1 kilogram wheels, and a second bike that has a 9 kilogram frame and 1.5 kilogram wheels. Both bikes have the same total 12 kilogram mass, so 1.5 times 2 plus 9, 1 times 2 plus 10, both 12. We want to know what is the kinetic energy of both bikes if they're ridden at a speed of 12 meters per second. They each have two wheels and they each have hoops with radius, or the wheels can be treated as hoops in terms of my moment of inertia of radius of 35 centimeter. Is it more advantageous to have the lighter frame or wheels explained? So that's a little piece at the end. So first of all, we have to account for the fact that we have two different bikes. So let's look at bike 1 first. And since the wheels are rotating and the bike is moving through space, we're going to have a situation where the total kinetic energy of bike 1 will be its rotational kinetic energy, the rotational kinetic energy of its wheels, plus its translational kinetic energy. Well, we know its translational kinetic energy is just going to be 1/2 the mass total times its v squared, so the v of its center of mass as it travels through space, plus we have two wheels on each bike. So the rotational kinetic energy of each wheel, which since they're the same dimensions in terms of radius, in terms of mass, will be the same. So I'm going to have 2 times the moment of inertia of the wheels times the omega of the wheels squared plus the 1/2 mv squared of the bike traveling through space. And this is the total mass, bike and wheels included. Okay? Now, let's look at bike 2, and let's set that one up at the same time. Let's go another color, bike 2. Yeah, you can see that okay. So the kinetic energy of bike 2 will be the same. The rotational kinetic energy of 2 plus the translational kinetic energy of bike 2. In this case, this will be 2 times I omega squared for, now we should differentiate this, let's call this I2 omega 2 squared plus 1/2 m2 total v2 squared. All right, well now how are we going to figure this out? Well, first of all, we have the I that we have to figure out for each wheel. So if it's a hoop with a certain radius, the moment of inertia for a hoop is going to be just mr squared. So in this case, this is the tire itself, right? We're treating the tire as a hoop of radius r. So the mass of each tire is 1 kilogram. The radius is 0.35 meters squared, so the I of bike tire 1, if we calculate that out, will be 0.1225 kilogram meters squared. Let's do the same thing for bike 2, where we have slightly different mass, so it's going to have a slightly different moment of inertia. They're also hoops, m2r2 squared. The radius is the same, but this will be 1.5 kilograms times 0.35 meters squared. So the moment of inertia of my second bike is going to be, or the tires on the second bike, 1.18375 kilogram meters squared. So greater moment of inertia, smaller moment of inertia. Okay, so what else do we need to know? We know that they're going to be moving at 12 meters per second. So that's going to give me my velocity here. We know the mass total. We need to figure out the omega. So here's where it gets a little tricky. But the omega for a tire that's moving through space can be related to the linear velocity of its center of mass through the omega equals v over r, so long as the wheel's not slipping. So you can think of it as a point on the edge of the wheel that's constantly in contact with the ground is also moving forward at the same speed as the center of mass. And that point is also on the wheel, so it can be related through this no-slip condition. This is also a no-slip condition. no slip between the tire and the ground. So if we calculate out our omega here, omega will be the v of the center of mass, 12 meters per second, divided by the radius, 0.35 meters. So my omega will be 34.3 radians per second. And if we think about what's going on over here, I have the same speed for each, the same radius for each, so the omega 2 will be the same as omega 1, which will also be 34.3 radians per second. Okay, so now I have everything I need to substitute and solve. So k sub 1, let's just try to figure out what's different, right? The only thing that's different is the moment of inertia of bike 1 is less than the moment of inertia of the tires of bike 2. But the omega is the same, the mass total is the same, and the speed is the same. So right away I should know that bike 2 is going to have slightly more kinetic energy than bike 1 will. Okay? So let's multiply this out. So 2, I have point, I'm going to cheat a little and not put in the units just for sake of fitting this all on here. 2 times I times omega squared plus 1/2 times the total mass, which is 12 kilograms, times 12 meters per second squared. So if I do this calculation, I get 144 joules plus 864 joules, which will be a total kinetic energy of 1,008 joules. Okay? Notice most of the kinetic energy is in form of the motion of the center of the mass. Less of it is in terms of the rotational kinetic energy of the wheels. All right, for the second one, for the second bike, same thing, but 2 times a different moment of inertia, 0.18375, don't lose the 3, times 34.3 radians per second squared, plus 1/2 times 12 times 12 squared. And the only term that's going to be different is this first term, which instead of being 144 joules, now I have 216 joules of rotational kinetic energy plus the same 864 joules of translational kinetic energy for a total of 1,080 joules. All right? Now, which of these is more advantageous to have, the lighter frame or the lighter wheels? So if we look at this, both bikes are moving at the same speed. So you're going to get to your destination in the same time on either bike if you're moving at the same speed. But the one with the heavier tires has more rotational kinetic energy. Because of that, it's going to have more kinetic energy than the smaller wheeled bike, meaning K2 from conservation of energy will require more chemical energy to convert and do work into kinetic. So you're going to have to work harder on bike 2 because you're fighting against the inertia of the wheels as well as the inertia of the entire bike than you will have to with bike 1 in order to get the same speed, to get to the same distance. So in general, what's better on a bike in terms of energy transformation, in terms of requiring less chemical energy to convert to the same amount of kinetic energy, it is to have the light wheels. So if you have lighter wheels, then less rotational kinetic energy is required for obtaining the same speed. Therefore, you're going to use less energy. And that's a good example problem for combining both translational and rotational kinetic energy.